Good afternoon to all. It's about 3 o'clock Eastern Standard Time, and we will be commencing our webinar shortly. Just we'll give about 5 minutes for people who are joining in, and we will start in just about 5 minutes. Thank you. Okay, good afternoon and welcome to this webinar on wireless power transfer from electromagnetic works. My name is Arvind Krishnan and I am one of the application specialists here at EMWorks. Today I will be taking you through this demonstration come webinar on this particular topic. Okay. Just let me briefly tell you the agenda for today, but before we do that, I just want to alert you that there will be a Q&A session at the end of this particular webinar. So if you have a question as we proceed, please don't hesitate to type it in your chat window. There is a chat window where you can type in your question and we will be answering them towards the end of the webinar. So you don't have to wait till the end of the webinar. So if you come across a question that you should ask us, please go ahead and type it in and we will answer them towards the end. Now going over the agenda, we'll start with the topic for the day, which is wireless power transfer. We will also talk about the offer that we have for new customers of EMWorks. Then we will deeply look into the wireless power transfer, how it is done inside EMWorks, EMS, and we will also look into the outputs that one can get from EMS. Finally, we will, I will show you a similar example using EMS and SolidWorks 2016, where you will get a good idea of how the product can be used. And finally, we will end with the capabilities that are there inside our product, and then we will jump right into a Q&A session. Okay. So without further ado, I'm going to go ahead and start this webinar. Okay. And as you know, the topic for the day is something about wireless power transfer or wireless charging. Okay. Pretty much today, most electronic equipments have become wireless. So thanks to Bluetooth technology and thanks to wireless communication, etc., most of our electronic devices are pretty much wireless. We take that for granted now and it's become quite ubiquitous. Along the same lines, as you can see in the picture on the right, wireless charging has also become quite a very important mode of transfer of power in latest, as far as the latest technology goes. So some of the benefits that wireless charging accrue to you is the ability to be able to charge multiple components using a same device, like a charging platform, the ability to be portable and to take it across wherever you want, and also from an aesthetics point of view, it makes a huge difference to be having some charging stations that are aesthetically appealing. So, and other than that, there are probably a lot of other applications which require charging remotely where you cannot have things in contact, or you will not be able to carry the power. So the idea here is to explore how wireless charging can be accomplished using EMS for SolidWorks. Before we go there, I just want to let you know that we have a special offer, promotion offer for people who are attending this webinar today. So normally the EMS magnetic license, which enables you to do wireless charging, sells for about $15,000 US, which is the permanent license. And then for today's offer, especially for the attendees of today's webinar, we're going to give a $5,000 off, and that comes to about close to 33% discount. And you can get this license for $10,000 US. Except that there is a small catch here, and you will have to act before August 15th, 2016. So if you are interested in knowing more about EMS and also acquiring a copy of the license, please do give us a call. The number is here, or send us an email at sales@emworks.com, and we'll be very happy to get in touch with you and provide you with this offer. Now let's jump on to our topic, which is wireless power transfer inside EMS. Okay. So how is this wireless charging or wireless power transfer enabled? It's actually enabled due to a principle of inductive charging. It's actually a very old principle, and the principle goes briefly as such. Then there are, say you have two coils that are separated and they're in the proximity towards each other. One coil is called the transmitter coil, and the other one is called the receiver coil, as you see in the figure in the PowerPoint. Okay. In the transmitter coil, if you supply, say, alternating current at a very high frequency, and we will later, I will explain to you the importance of the frequency of the current, then due to the principle of induction, you will get some amount of induced current and voltage in the receiving coil, although there is no contact between the transmitter coil and the receiving coil. And this principle of induction is what enables us to do wireless power transfer or wireless charging. Now the induced current now that comes in the receiver coil can actually be used to charge a battery or to run a load, etc. Now we can do wireless power transfer like this over very short distances. If the coils are within close proximity towards each other, then we use coils. But at the same time, wireless power transfer is also enabled over very long distances or medium distances, and that is done using transmitting and receiving antennas instead of transmitting and receiving coils. Okay. So as far as the distance goes, if you have short proximity, which will be the subject for today's interest, we will use coils to enable that. If you have to transmit power over long distance, then you can accomplish the same using what is called as antennas. Okay. For both these problems, our company, Electromagnetic Works, we have a solution, and we will look at what can be used depending on your application. So what we will focus for today's presentation is wireless power transfer within short distances. And this can be accomplished, as I said before, using coils. And we can use what is the program that we can use to study this is called EMS for SolidWorks. Okay. But if you are interested in, say, wireless power transfer over long distances using transmission and receiving antennas, we can also study the efficiency and the effectiveness of such an antenna using a product called HFWorks, which is also from our company. Okay. Today we will focus our discussion on the EMS part of it, and the HFWorks is something that we can take up on a later day. Or if you have interest in that, just type it down in the chat window. We'll probably talk to you later about this topic. Now let us understand what is of interest to engineers. Okay. So people who are doing wireless power transfer, wireless charging over small proximities using coil, for example, they are very interested in what kind of coils do I have to use, what's the design of the coil, how many turns should I have, what's the wire gauge, etc. Okay. The second thing that they would be interested in knowing is, based on the design of the coil and the geometry of the coils and the proximity of the coils, they would actually need to know what's the efficiency of the wireless power transfer. So if I supply, for example, 1 unit of energy in my transmitting coil, how many units of energy can I actually get in the receiving coil? And that's the ratio of what you can get to what is being supplied is crudely can be termed as efficiency. So engineers will be very interested in knowing what's the efficiency of wireless turbines. Needless to say, higher the efficiency, the better is your charging devices, better is your design. Then one might be interested in the electrical characteristics of the coil. What are the inductances of the coil? What are both the self, mutual, the leakage inductance? What is the coupling coefficient between the two coils, etc. And finally, if there are any losses as a result of heating, the current losses or the ohmic losses in the coil, that might end up in heating of the coil. Okay? It's a good idea to understand that, so that we know for sure that the heat is not, it's something that's manageable. In the case of wireless power transfer over small proximities, I don't think heat will be a big problem, but nevertheless, if that's of interest, that can also be studied using EMS. Now, all of these above things that I mentioned here can actually be observed and studied using the product EMS. Now let's briefly take a look at the steps involved in accomplishing such a task of, say, trying to study a mechanism by which we can do a wireless power transfer. As you can see in the picture towards my right, you have what is called as the power transmitting coil. That's a coil that transmits power, okay, energized. And you also can have a receiving coil, as you see here. The coil that's brown in color is the receiving coil. The receiving coil helps you to collect the induced current, which can be then used to run a load or charge a battery, etc. Now the creation of the model can be accomplished using CAD. For EMS, for SolidWorks, SolidWorks will be the CAD platform that will be used. Nevertheless, irrespective of the CAD that you use, we will be able to take in any CAD geometry inside SolidWorks, and we will be able to perform simulation using that. Okay. Next step would be to create a magnetic study. Now we would use EMS for SolidWorks for this particular purpose. Then we can create coils inside our program EMS. We can run the simulation, we can look at the results and so on. So briefly, these are the steps involved. Later, as I show you the product, you will actually get a clear idea of each of these steps. Now the coils that we use for this particular simulation, okay, is going to be, it's going to follow these things. So we're going to have a transmitter coil. That's going to be a planar circular coil with wire gauge of 18 wire gauge copper. Okay. It's going to have an outer diameter of 42 millimeters, inner diameter of 20.81 millimeters. It's going to have 10 turns of copper, and it's just going to be a single layer coil. The receiver coil, on the other hand, is going to be a spiral coil, as you see here in the solid geometry. It's going to have a 15 wire gauge material made of copper again. The inner and outer diameter are specified here, and we're going to have 5 turns of the coil. So we're going to study and understand how effective is this particular configuration for wireless power transfer. Now when we are doing a simulation, it's a good idea to have some objectives for the simulation. Now some of the objectives for our simulation today are the following. First of all, we would like to understand what are the electrical characteristics of these coils. For example, what is the inductance of the coil? What's the coupling coefficient between the two coils given a particular position? Okay. The next thing we would like to know is to understand what are the ohmic losses in the coil. And the ohmic losses is basically the I squared R losses that might result in heating, but that's also is the amount of power that is actually supplied or received by these coils. Okay. Then we would like to understand how much of induced voltage is there in the receiving coil. And finally, we can understand the magnetic field, etc., and the distribution of these, the current density, the magnetic field density around generated by these coils. These are some of the simulation objectives. that we will be looking at today. Now let's take a look at this example inside EMS. So let me go ahead and quickly introduce you to our product EMS for SolidWorks. As you see here, I'm inside a familiar SolidWorks environment. Okay, this is SolidWorks 2016. Now here I have just the image that I showed you. Now I have them as solid models. I have a power transmitter coil that you see here highlighted in blue, and that's just that has a cross section. As you see here, this is the cross section of that coil. Now this, next we take a look at the receiving coil. Now the receiving coil is a spiral which is drawn out inside SolidWorks, and you can see the cross section, which is actually a circle of the receiving coil. Okay. Now the objective is, if I send some particular, if I send excitation through the transmitting coil, what is the amount of voltage that I will receive in the receiving coil? How much is the efficiency? What's the coupling coefficient, etc. These are some of the objectives, as I mentioned earlier, that we will be able to study using EMS. Okay. Now there's one important thing as far as, let me go ahead and show, is the geometry of air. Okay. EMS is actually a finite element type of program that will help you to solve for, it's a 3D field simulation. Okay, so you can actually get the magnetic fields, etc. at every location inside this particular cylinder that you see here, and this cylinder represents the air volume around the coil. So this is one of the crucial and important step in the in doing your simulation, is to create air geometry around your model, and that's also done using SolidWorks. So let me go ahead and hide this air geometry. And let's zoom back to our model of interest. Now we've got two coils and air geometry around. Now it's we are ready to take a look at EMS for SolidWorks. Okay, EMS for SolidWorks is a gold certified partner product for SolidWorks. What does this mean? It means that EMS works seamlessly inside SolidWorks with SolidWorks models. You do not have to, when you create your models in SolidWorks, it becomes ready for simulation using EMS. There is no hassle of exporting your model and taking into a different window and so on. Okay, and these are some of the gold certified standards that vendors must meet, and EMS is probably the only gold certified electromagnetic simulation software for SolidWorks. Now the EMS manager that you see here right inside SolidWorks helps you to do your simulations. Okay. Now the simulations inside EMS is done is actually maintained as separate studies. Now as you see here, I've got a study which I named it as 125 kilohertz. That's the frequency of the input signal. Okay. Now how does one create a study inside EMS? You can just create a new study inside EMS by right clicking on the top level and create a study. Now you can look at the various different study options inside EMS. Okay, EMS can help you to do magnetostatic if you only have DC as your current, and if you have permanent magnets, we can do magnetostatic. EMS can do AC magnetic. In this particular example, we will use the AC magnetic module of EMS. AC magnetic, if you have, as the name suggests, if you have AC excitation, you would use AC magnetic. And transient magnetic, I would say, is pretty much the father of all of the magnetic studies. That can help, that can do both DC, AC, and any varying time signal as a function of time. It can be pulse, it can be rapidly decaying, it can be any kind of current or voltage versus time can be accomplished using transient magnetic. Or also you can have permanent magnets, etc. to do this. In addition to this, we also have some electric modules, electrostatic, electric conduction, and AC electric. That's not something that is in the topic of interest today, so we will just skip that part. But if you have some questions about those modules, please type it in and we will be happy to answer them towards the end. Okay. Now you can create a AC magnetic study. Some of the things that is of interest is going to be, one is called the parameterization. EMS has the ability to modify SolidWorks geometry and study the results of simulation as a result of varying geometry. So any dimension inside SolidWorks can actually be treated as a parameter, and EMS can do many design scenarios by varying the geometry of those parameters. In addition to it, EMS can be coupled with thermal simulation, it can be coupled with structural simulation, and it can be coupled with motion simulation. So all of these coupling analysis is available in EMS. For this particular study, we will create what is called as an AC magnetic study. Once the study is created, notice that it creates a study tree as you see here. Now the next step after creating the study is to define materials. So here the power transmitter coil is made up of copper. So obviously I select all the bodies that comprise this particular material and I right click and say apply material. Now EMS comes with its own standard material database. So we have got a lot of materials as you see here. We have conductor materials which has copper, aluminum, etc. We also have steels. We have a lot of steels with its with their own properties. Okay. We also have ferromagnetic materials, which is true permanent magnets, semiconductors, substrates, ceramics, etc. So most of the materials that are used in this industry will be present in the material database. However, the material database is also fully customizable, so if you have to define your own materials, you can do so easily and use it for simulation. So in this particular example, we use copper as the main material, so because all the coils are made of copper, and then air geometry is made of air. So once after defining the material, it's now time for us to understand how coils are defined. Okay. So as far as defining the coil, we will start with the transmitting coil. The transmitting coil is a wound coil, and I define that by selecting the components that comprise the transmitting coil and also selecting the area of cross section through which the current is applied. Okay. So this is the area of cross section. As you see here, you need to select the coil and the area of cross section. Once you do that, you have to specify the number of turns. As we saw earlier, we had 10 turns in this, the wire gauge, and also the RMS value of the current that is there in the transmission coil. Okay. So the RMS value of the current is also specified in the definition of the coil. Now this is the transmission coil. Now how about the receiving coil? Now the receiving coil is what is known as a passive coil. There is no excitation of the receiving coil. The receiving coil is, you receive induced current in the receiving coil. So EMS can help you easily define these kind of passive coils. So the receiving coil is defined as a solid coil because we have drawn out all the cross section and all the turns of the receiving coil. You specify the solid body that comprise the receiving coil. You specify an entry and an exit. So it's basically the two ends of the receiving coil. And when you come to the properties here, you just specify a net current of 0 amps. Now what this tells EMS is that, hey, there is no excitation of this coil. It's just a receiving coil, and you need to figure out what kind of induced currents and voltages are there in the receiving coil. Okay. Now as far as coil definition is concerned, this is it. Let me just recap. So as far as creating a simulation inside EMS is concerned, it's very easy. Once you have your geometry that you do it using SolidWorks, you have to create a study. After creating a study, we define the materials of each of the components. After defining the materials, we come to coil. We define the wound coil or the excited coil. And then finally we define the passive coil or the coil where you're going to receive the induced current. Okay. Now EMS is a finite element based 3D field simulation software. Okay. So everything in finite element base is done through what is called as meshing. Now EMS has automatic meshing features which helps you to create a finite element mesh. I'm going to just show it automatically based on the geometry. Now this is the finite element mesh created by EMS. Now let me go ahead and hide the mesh. In addition to creating the mesh, you also have ability to control the mesh in each of the geometry. For example, if I have to specify a mesh size for a particular geometry, I can do so very well in EMS. So here I pick the geometry or the face in which I would like to have a different mesh size, and then I specify the element size for that particular geometry. In this case, I've applied a mesh control for both the transmitting and the receiving coil. Okay. Now, once this is done, we are ready to solve the problem. In the interest of time and for this demonstration, I have already solved this particular problem, so we will just jump straight ahead and look at some of the simulation results. But as far as the solvers of EMS are concerned, I would like to bring to your notice that we make use of multi-cores and multi-processors in your machine, and there is no separate charge or any kind of additional fee or charge for this. It comes standard with all EMS licenses. We use multi-core, and it will use the RAM in your machine as well. So if you have a multi-core processor or a multi-processor machine with 8 or 16 GB of RAM, it's going to optimize and use most of your resources to run this problem quickly. Okay. So a problem of this kind takes about 10 minutes to solve. So in a machine that has about 2 cores and about 4 GB of RAM. Okay. Now, how are the results in EMS organized? So let's first take a look at some of the results. All the results inside EMS are organized in the form of what is called as a result table. Now when I right click on the result table, I get a wealth of information. So the first thing that if you go back to our objectives, one of the first thing I said is to be able to understand the electrical characteristics of my coil. What are the inductance, etc. Now EMS gives you those values. You can calculate the inductance, or even what we call as the inductance matrix of the 2 coils here. So the wound coil has a self-inductance and the solid coil has a self-inductance, and this is the mutual inductance. So EMS gives you both the self and the mutual inductance of the coils. After that, EMS also will calculate the leakage inductance if it is of interest. That is also being automatically calculated by EMS. Once that is done, let us go quick to some of the things that is of interest to us. The next thing is the coupling coefficient. As you see here, the coupling coefficient here that is calculated by EMS is about 0.23 or 23%. Now what this means is that 23% of the flux that is generated by the transmitting coil is actually cuts through the receiving coil. So obviously the geometry of your coils and the proximity dictates what this coupling coefficient is going to be. So it's all the geometry, so the size of the coil, the number of turns, etc., all of it determines what the coupling coefficient is. So you would ideally you would like to have as high as a coupling coefficient as you can. Okay. After that, let's jump straight into the induced voltage. Now for this particular example, we get an induced voltage of close to 89 millivolts in the receiving coil. Okay. Now we can also take a look at the solid losses. So basically this is the I squared R loss. So that's close to about 3.2 milliwatts. 3.3 milliwatts is the solid loss or the I squared R loss in the receiving coil. Obviously, as far as the winding coil, as far as the transmission coil is concerned, we supplied RMS value of the current. So I squared R losses, winding loss here is here. It's about 1.9 and 1.9. 3.8 watts is pretty much the winding loss. Okay. 3.8 milliwatts. Sorry. So another way of interpreting these winding losses and solid loss is how much of energy is actually being transmitted. The amount of energy that is being sent to the transmission coil is about 3.8 milliwatts, okay, and the amount of energy received by the receiving coil is about 3.3 milliwatts. So you can see that almost more than 70% of the energy that is transmitted is actually being received. So as a result, one can have an idea of the efficiency of this power transfer, okay, which is basically 3.3 divided by 3.8. Next, I think pretty much we have covered, and as you see, EMS can give you other things like flux linkage, the winding losses, the resistance in the coil, the energy, etc. So this EMS result table is a very important thing. Almost all the engineering quantities are automatically calculated and stored in this result table. Now after that, let's now move on to take a look at some 3D visualization plots. Okay, so the one thing that people are interested in is to understand what is the magnetic flux density in my model. So you can actually take a look at it. And here is the section plot of the magnetic flux density through my model. So here I can actually cut the model and take a look at it from a section point of view to see what's the magnetic flux density in my model. And you can also do it for the entire solids, as you see here, without a section plot. And you can see, you can just read off the values here. You can, and what these 3D plots show you is the high areas where the values are high, areas where the values are low, and so on. Okay. In addition to the magnetic flux density, you can look at the magnetic field intensity. And the next thing that is of good interest to us is the current density. Okay. So let's take a look at the current density. Here is a section plot of the current density in my receiving coil. Obviously, as far as my transmitting coil goes, we exactly know how much current we put in, so it's not a big deal to understand what's going on in the transmission coil. But in the receiving coil, it's very important because there it's a passive coil. We would like to collect current here, and this is the distribution of current across the cross section of the receiving coil. You can understand that the current tends to distribute itself towards the outer edges of the coil, and that's because the frequency with which the current is sent is about 125 kilohertz. Okay? So this is the distribution of the current in the receiving coil. And you can also take a look at the current density actually as a whole. You can see the current density is pretty uniform in the transmission coil. And as far as the receiving coil is concerned, this is the distribution of the current. So basically, EMS can help you understand a lot of these quantities, both visually as well as in terms of your parameters, electrical parameters that you saw in the result table. So what happens, how does now this transmission efficiency I told you is really a function of the frequency with which the transmission coil is being excited. Now, you know, one way of studying that is to understand what happens if we just excite the transmission coil at regular 60 hertz or 50 hertz frequency. Would we get similar results? And we've studied that, so I've created another simulation. So notice here that EMS can organize your simulation studies, and it can actually keep track of various simulations within the study tree. Now in this particular study, what really happens at 60 hertz? So let's take a look at the result table again. And let's pay attention to the induced voltage. You noticed here in the previous example we had several millivolts of induced voltage. Now you're basically having you know 3 orders of magnitude lesser as far as your voltage is concerned. So another nice feature that is there in EMS is for you to have the ability to compare results. You can actually compare results between studies. So I can actually open the result table of this one and take a look at the induced voltage. You can see here it's about 89 millivolts is the induced voltage when you have 125 kilohertz, and if you have when you have 60 hertz, the induced voltage you can see is 45 into 10 to the 6 minus 6 volts. Okay. All right. So you can compare results here, and there are also other things that you can see. The efficiency. If you look here, winding loss, which is basically the amount of energy that is there in the transmission coil, is about again 3.8. That doesn't change. But if you look at the solid losses, you can see how poorly you only get about 3 e to the minus 9 watts of receiving energy. So you can see the efficiency is really horrible. It's close to almost nothing. So and that's the effect of frequency on this whole thing, and it's very important. That's why you have to be able to do the simulation at very high frequencies, because people who use this wireless charging and wireless power transfer tend to go towards kilohertz, megahertz, and EMS can deal all the way up to several hundred megahertz frequency. We will be able to do that simulation. Okay. When you talk about wireless charging over very long distance, you're talking about antennas. We are now going into several hundred megahertz, gigahertz, and you would require another product or high frequency HFWorks product to do that type of simulation. Okay. Now pretty much let's get back to our slide, and I want to just recap on some of the results that we saw. So if you look at some of the simulation results that were there in the result table, you've got the inductance values are there, coupling coefficient is computed, then you also have the transmission receiving coil, the power, and then you can get the induced voltage, which is about milliwatts, okay? And close to the efficiency is over 70%. And we also saw that we got some 3D plots, and I've just given you a set of 3D plots that can be got using EMWorks. The magnetic flux density is possible both as a section and in the 3D geometry as a whole. You can also look at the current density in the receiving coil, and also look at the magnetic flux density even in the air surrounding the region, as you see in the plot, the fourth plot here in the down in the column. Okay. These are some of the 3D plots that can be obtained using EMS. Now I noticed that we probably covered very small segment of application that EMS can do. This is a general slide. I'm just going to keep it for your interest, not going to read through all of them. This tells you all the application and industries that EMS and HFWorks can actually tackle. So on your left hand side you see the low frequency product that, as I said, goes all the way up to several hundred megahertz, and the high frequency product which can do up to several gigahertz. Okay. Now the product here is called EMS, and the supporting product here is called HFWorks. And you can see here EMS is basically an electromechanical type of design, and HFWorks is mainly for electronics, passive, RF and microwave components. Okay. For EMS, here are the applications. So basically from motors to coils to magnetic record, levitation, recording devices, solenoids, etc. can be done. Okay. As far as HFWorks is concerned, you can do antenna simulation, couplers, filters, basically all passive RF and microwave components. Okay. And for the benefit of people who came in joined us a little late, we are recording this particular webinar, so we will be sharing the recording with you, okay? And where you will have access to all the slides that we covered so far. Okay. Now again, I'm just going to reiterate here, we have a special offer, and we want to thank you for attending today's webinar. We have a special offer here from EMS. Now, the cost of our license, permanent license, comes to about $15,000 here, but for we have a special offer for today's attendees. We're giving you a $5,000 off. Okay, so the price of EMS magnetic permanent license is going to be $10,000, and this includes 1 year of maintenance and all software upgrades in that 1 year. There's only one catch here, is this special pricing lasts till August 15th. So to avail this, please contact us. Here is the number before August 15th, and our sales team here will help you make a purchase in this particular special price. So with this, I'm going to go ahead and turn on the floor to some Q&A. But before we do that, I would like to know if my colleague, who is our sales manager, Adam, has a few words to say. If not, we can go back straight to our question and answer session. So I'm going to make Adam our presenter. So if he has a few.
Arvin?
Yes, Adam. Can you repeat it, please?
Yeah, thank you so much for all of that. The only thing I wanted to add that they also can send an email to sales@emworks.com. Sales@, we'll write it here in the chat box. Sales@emworks.com if they want to inquire about this price offer. And if you can, please proceed to answering questions. I think there's quite a few of them.
Okay, no problem. So we're going to answer the questions in the order of it came. So let's go ahead and go to the Q&A sessions. Okay. One of the questions that was asked is, can adjacent electronics and coils and ferromagnetic substances interfere with the transmission? The answer is yes. Obviously, there is going to be, whenever you have a power transfer, we would like to, as many conductor materials that are not directly involved in this power transfer should try and stay away from the vicinity. So obviously, if you do have some conductor ferromagnetic substances, it is going to affect the efficiency of your power transfer. And EMS can actually study this kind of interferences, so you can stick in objects and you can understand how the efficiency of power transfer actually is eroding as a result of some unwanted ferromagnetic and conductor materials. The next question is, does the EMS license include help and PDF manuals? Yes, absolutely true. The license of EMS comes with its own online help. We have a complete online help topics, okay? And this is available both as PDF as well as a HTML base. Actually, our online help is also right on our website. So this is available online for anybody with an internet connection. It's available. It also comes with a set of tutorials. Actually, we have a lot of tutorial examples where one can learn EMS by themselves using these things. In addition to it, we also have a new feature called EMS Demo Viewer. Now, EMS Demo Viewer is also, like I would say, a very extended tutorials where a lot of real-life examples are continuously updated on almost a weekly or a monthly basis, where users can download these models, and here you can have there's a getting started lessons, there are tutorials, there are user-defined examples, and there are examples pertaining to various applications, and also some of these examples have step-by-step instructions, video tutorials, etc. So EMS Demo Viewer, I would say, is our future learning resource that one can use to do this, learn EMS. In addition to it, we have over 60 videos in YouTube. We encourage you to take a look at it. And finally, we encourage you to take a look at our website, emworks.com, where you can get customer testimonials, past successes, some access to these videos, access to our help, etc. Then we have another question. What boundary condition approximation is used on the air exterior surface? Okay, you notice that we created an air geometry, let me just refer back to the model. The air geometry here, which is extremely important to doing any kind of electromagnetic simulation, because the magnetic field exists in the air and we would like to capture it. So automatically EMS takes care of the boundaries of the air, extremities of the air geometry. So you don't have to specify any boundary condition. We automatically take care of the extremity boundary conditions into the equation. Now one thing that needs to be explained here, this is more technical, is you have to consider the air geometry big enough so that the extremities of this air geometry, the field values are very, very less compared to the maximum field values, and the variations in the field in the air extremities is also less. So you got to make sure that you take in the right size of the air box, and once you do that, all the automatically we enforce constraints on the outer geometry, outer nodes to take care of this one. So the other question that was asked is, can you optimize the analysis based on one parameter? Okay, let me answer this. Actually, because we have opened here, I have a design scenario study also done using the same model, where we varied the distance between the two coils, and you would like to understand how things vary as you vary the distance. Okay, so now you have what is known as the design scenario. Now the design scenario, you can take in any parameter, which is any geometry parameter, any dimension, any mate values, any values that you can input inside SolidWorks can actually be used as a parameter. Now you can vary these parameter values, and you can study how effective, you can study the results for various parameters. Now coming back to optimizing, we can give you an entire solution space where you will probably have to pick an optimal, I would say, a geometry parameter. So do we optimize automatically for the customer? No, but you can study an entire solution space, and you can see which one, which geometry value, which parameter value comes closest to your target, I would say your target. So that's how EMS takes care of optimization. Okay. Also, there's a question about approximately how long was today's simulation on a 16 GB or 32 GB RAM 8-core computer. As I said before, I'm running this on a 8 GB RAM quad-core, I think, dual-core processor, and it took about 10 minutes to do this particular problem with 125 kilohertz, 10 minutes for 60 hertz, and then parametric study is 3 different solutions. So a typical simulation of this kind will take about 10 to 15 minutes. However, on a 62 or a 32 GB RAM machine, obviously the time taken is going to be much lesser, in the order of a few minutes is going to be. Does EMS support non-planar coil like hemispheres? Absolutely. EMS can support any geometry that you can draw inside SolidWorks. So if it is hemisphere, if it is any kind of geometry that you can envision and you can draw as a solid model, EMS will readily support that. I think with this pretty much, I think I've answered most of the questions here. Okay, there is also one more question. Can you get graphical representation of the simulation that involves moving electromagnetic parts? Absolutely. Absolutely, you can do that. For this, I'm going to just revert back to the slide here about EMS. If you look at the functions of EMS, so probably we don't have this here. So the EMS can be coupled with several types of simulation. EMS can be coupled with thermal, EMS can be coupled with motion, and EMS can be coupled with structural. So EMS coupling with motion is the one that is required for electromechanical simulation. So for example, if you have solenoids, if you have things that move and you would like to co-simulate movement along with electromagnetism, EMS can do that, and it does that with SolidWorks motion. So if you have SolidWorks motion and EMS with motion add-in, you will actually be able to simulate moving solenoids and things like that. Okay? So you can get a graphical representation of a solenoid moving, or there are many examples. I encourage you to take a look at our YouTube channel and you will find some examples related to these things. So EMS can do moving parts as well. So with this, I think we come to an end of this particular presentation. On behalf of everybody here at EMWorks, I'm going to thank you all for taking the time today to attend this particular presentation. I hope this presentation was intuitive and was a little bit educative for you, and we sincerely hope that EMS can find a good value in your organization. You can make use of EMS to design better products. So if you are interested in EMS, please take a look at our website, our resources in YouTube, and feel free to give us a call if you would like to talk to our application specialist to discuss your particular application and how we can help you solve your problem. Please contact us. Our telephone numbers are given here. The 1-800 number is for anybody calling from North America, but if you're calling from everywhere else in the world, there is this number. And always you can write us an email, sales@emworks.com. You can contact us. I'm just going to put that, sales@emworks.com, and we'll be very happy to get back to you. And if required, we will call you and talk to you regarding your needs. Okay. Again, I want to wrap up by thanking you all, and just to remind you that we do have an offer for everybody who has attended today. So at some point of time, if you would like to explore more how EMS is going to help you, and if you want to make use of this offer, just give us a call and we will be happy to help you with that. With that, I'm going to end this particular presentation, and thank you very much and have a nice day.